Right now, as you listen to this, there are 5 working machines further from the Sun than Neptune, and not one of them is ever coming home. We explain that as a budget decision. Nobody paid for a return ticket. It is not a budget decision. Every account of space travel you have ever heard is organised around distance, and distance turns out to be the one quantity that barely matters. Entering orbit around Mercury costs more than leaving the solar system altogether. The record for surviving on the surface of Venus is 127 minutes, set in 1982. The only oxygen ever manufactured on Mars comes to 122 grams, against the 30 tons a crew needs to leave. 8 planets, and 8 completely different reasons the second half of the journey fails. By the end of tonight, you will know exactly what would really happen on a journey to each planet, and which one is the world you never return from. Get comfortable. If you are the kind of person who enjoys watching a familiar idea come apart under a few specific numbers, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this, the distance to another planet will not be the number you think about first. Now, let's slowly settle in. Human beings have arrived at every planet in the solar system, and human beings have come back from none of them. That sentence is doing something slightly dishonest, and I want to unpick it before we go any further, because the way we untangle it is going to shape everything that follows tonight. What has arrived at every planet is machinery. Small, patient, extraordinarily clever machinery, built by people who mostly never saw the images it sent home. Mariner, Venera, Viking, Voyager, Galileo, Cassini, Messenger, Juno, New Horizons, Perseverance. Between them they have touched, orbited, photographed, tasted and listened to every major world between the Sun and the outer dark. Not one of them was ever designed to come home. Not one of them ever did. We tend to treat that as a budget decision. Of course the probes did not come back. Nobody asked them to. They were cheap in the way a one-way ticket is cheap, and bringing them home would have been an extravagance nobody could justify for a few kilograms of instruments. That explanation is comfortable, and it is also mostly wrong, and the reason it is wrong is the reason we are here tonight. The probes did not come back because coming back is not the same problem as going. It is not a harder version of the same problem. It is a different problem, with a different shape, and at every single world in this solar system it fails for a different reason. Here is the thing that almost nobody tells you when they talk about space travel. The number everyone quotes is distance. How far is Mars? How far is Jupiter? 225 million kilometers, 780 million kilometers, 4.5 billion kilometers. Those numbers get printed on diagrams and read out in documentaries, and they are all correct, and they are almost entirely useless for understanding what a journey to a planet actually costs. Distance is not the currency. Distance is a description of where things are. It is not a description of how hard it is to get to them. The currency of spaceflight is velocity. Specifically, it is a quantity engineers call delta V, which simply means change in velocity, measured in kilometers per second, and which is the total amount of speeding up and slowing down a vehicle has to perform over the entire course of a mission. Every gram of propellant a rocket carries exists to buy delta V. Every maneuver spends it, and once it is gone, because there is nowhere out there to buy more. The strange thing about delta V, the thing that makes it so counterintuitive that it quietly breaks most people's mental map of the solar system, is that it has almost nothing to do with how far away something is. It has to do with how different your velocity has to be from the velocity you already have. And you already have an enormous velocity right now sitting where you are. The Earth is carrying you around the Sun at roughly 29.75 kilometers per second. That is not a small number. That is about 87 times the speed of sound. You're travelling at that speed at this moment, and so is everything on this planet, and so is every rocket that has ever launched from it. Because a rocket does not start from rest. It starts from Earth, and Earth is already moving very fast in a very particular direction. So when a spacecraft leaves for another planet, it is not setting off across a still landscape. It is stepping off one moving platform onto another moving platform, and the whole difficulty of the maneuver lies in the difference between the two speeds. Get that difference wrong, and you do not miss your target. You arrive at your target far too fast to stop. There is one more piece of arithmetic worth having in your pocket before we set off, and it is the piece that makes everything else in this video bite. The relationship between the Deltavia mission needs and the propellant it must carry is not a straight line. It is an exponential. Doubling the velocity change you require does not double your fuel, it squares the ratio, and the mass required climbs away from you far faster than intuition allows. This is why the obvious answer to every problem we are going to meet tonight, just bring more fuel, is almost never an answer. Extra fuel has mass. Mass needs fuel to move it. That fuel has mass of its own. Somewhere in that spiral the numbers stop closing, and a mission that looked merely expensive becomes a mission that cannot be built out of any quantity of money. Which brings us to the first inversion of the night, and it is a good one, because it is the kind of fact that rearranges the furniture in your head. Mercury is the closest planet to the Sun. It is one of the nearest planets to Earth in raw kilometers, and in delta V terms, in the only currency that spaceflight actually accepts, entering orbit around Mercury is more expensive than leaving the solar system altogether. It costs more to stop at the first planet than it does to never stop at all. Pluto, 4,000 million kilometers further out, is easier to reach. I want to let that sit for a second, because when I first properly understood it, I had the distinct feeling of having been handed a map drawn with the wrong ruler. The solar system that most of us carry around in our heads is a series of concentric circles where difficulty increases with radius. Nearby is easy, far away is hard, and the trouble scales smoothly with the kilometers. That picture is not a simplification of the truth. It is a different picture altogether. The real solar system, the one measured in velocity rather than distance, is a landscape of hills and valleys, and some of the steepest hills are the ones closest to home. We will come back to Mercury in a moment and see exactly what that cost looks like in practice, because the story of the one spacecraft that ever managed to orbit it is genuinely remarkable. But before we set off, I want to lay down the sentence that this entire video is built on, because I am going to say it again several times tonight, and each time it will mean something slightly different. Arrival is cheap, departure is not. At first pass that sounds like a piece of engineering trivia, and at first pass that is all it is. It costs less to fall towards something than to climb away from it. Gravity does half the outbound work for free and charges you double on the way back. Fine. Everyone who has ever thrown a ball upward understands this in their body. But it turns out that the sentence keeps deepening as you go outward, and by the time we reach the far end of the solar system tonight, it will have stopped being about propellant entirely. It will be about something else, something that has nothing to do with rockets, and I think when we get there, you will find that the whole shape of the journey has quietly changed underneath you. Because here is the question I want us to carry the whole way out, and I am not going to answer it until the very end. Somewhere on this journey, at one of these 8 worlds, the trip stops being a trip and becomes something else. Somewhere out there is the planet where you go and you arrive and you do not come back. Not because anyone chose that, not because of a budget line, but because the physics of that particular place will not permit the second half of the sentence. I want to find where that line is. I want to know which planet it is. That is what we are doing tonight. We are going to travel outward, one world at a time, in order from Mercury to Neptune. At each one, we're going to do the thing that documentaries usually skip. We're going to arrive properly, stand on the surface where there is a surface, sit in the atmosphere where there is not. And then we're going to ask the only question that actually matters, which is not what is it like there. It is what happens when we try to leave. And the answer, I will tell you this much in advance, is different at every single one. Mercury will not let you go for one reason. Venus will not let you go for a completely different reason. Mars fails a third way, Jupiter a fourth, Saturn a fifth. 8 worlds, 8 separate walls, apparently unrelated to one another, with nothing obvious connecting them except that they are all in the same solar system, and they all say no. Unless, of course, they are not unrelated. Unless there is one thing underneath all 8 of them, wearing 8 different disguises. By the end of tonight, you will know exactly what would really happen on a journey to each planet, and you will know which of these worlds is the one you never return from. I do not think it is the one you are expecting. I am fairly sure it is not the one I was expecting either when I started pulling this together. So let us begin where the map says it should be easy, and where the physics says it is anything but. Let us go to the small grey world closest to the Sun, the planet that takes longer to reach than the edge of everything. On the 3rd of August 2004, a spacecraft roughly the size of a small car left Cape Canaveral bound for a planet that is never more than about 222 million kilometers from Earth. It did not arrive until the 18th of March, 2011. 6.5 years. In that time it travelled something in the order of 7.9 thousand million kilometres, a path more than 30 times longer than the straight-line distance to its destination. And it flew past Earth once, past Venus twice, and past Mercury itself 3 separate times without stopping, before it was finally moving slowly enough relative to that small grey world to be captured by it. The spacecraft was called Messenger, and it remains one of the most quietly astonishing things our species has ever done, precisely because it looks from the outside like an enormous waste of time. 7,900 million kilometres of travel to cross 222 million. 6.5 years to reach the second nearest planet. 6 passes at 3 different worlds. And then, at the end of all of it, an orbit insertion burn that lasted 15 minutes. Why? Not because Mercury is far. Mercury is not far. Because of what happens to anything that falls toward the Sun. Think about what dropping inward actually means. The Sun's gravity is not gentle. Anything that moves closer to it accelerates, in exactly the way a ball rolling down a hill accelerates, and by the time a spacecraft launched from Earth's orbit has fallen all the way into Mercury's orbit, it is moving very much faster than it was when it started. It arrives at Mercury like a car arriving at a parking space at 200 kilometers an hour. The problem is not finding the space. The problem is stopping, and Mercury cannot help. This is the crucial thing. When a spacecraft arrives at Mars or Venus or Jupiter, there is an atmosphere waiting, and an atmosphere is free braking. You can fly into it, let friction take your excess speed, and pay for none of it in propellant. It is the single most useful gift a planet can give a visitor. Mercury does not have one. What Mercury has is a surface-bounded exosphere so thin that a given atom of hydrogen or sodium or calcium is more likely to strike the ground than to strike another atom. That is not an atmosphere. That is a rumour of an atmosphere. You cannot brake against it, you cannot glide in it, and you cannot use it for anything at all. Nor can Mercury's gravity do much for you. The planet is small, about 2,440 kilometres in radius, with a surface gravity of roughly 3.7 metres per second squared, a bit over a third of Earth's. It does not have the mass to reach out and grab a fast-moving visitor, so every single kilometre per second of excess velocity has to be removed the expensive way, by burning propellant or by spending years flying past other planets and letting their gravity steal your speed for free. Messenger chose the years. It gave up more than half a decade of its operational life to arrive slowly enough to stay. Now hold on to that, because here is the sentence that makes it land. Every kilometre per second that Messenger spent 6.5 years shedding is a kilometre per second that anybody leaving Mercury would have to put back. There is no 6-year gravity assist tour that works in reverse. You cannot borrow speed from a planet you're trying to escape. To leave Mercury and return to Earth, a vehicle must climb back out of the Sun's gravity well from a position deep inside it, unassisted, on its own propellant, from a world with no atmosphere to launch through and nothing to push against. Arrival is cheap. Departure is not. On Mercury, that is not a metaphor. It is a line in a mass budget that has never closed for any crude architecture anyone has seriously proposed. And the surface, meanwhile, is doing something remarkable while you try to solve it. Imagine standing there. You're at a point on Mercury's equator just before dawn. The ground under your boots has been in darkness for the better part of 3 Earth months, and it has cooled to something close to minus 180 degrees Celsius. Cold enough that ordinary steel would shatter rather than bend. Above you the sky is not dark blue or violet. It is black, absolutely, without gradation, and the stars are hard and steady in it because there is no air to make them tremble. There is no wind. There is no sound of any kind, ever, because sound needs something to travel through. Then the horizon begins to pale, and the sun comes up. And it is enormous, 2.5 to 3 times the width it appears from your window at home, and it rises with a slowness that is genuinely difficult to hold in your mind. Not minutes, days. At certain longitudes on this planet, because of the way Mercury's spin and its orbit interact, the sun climbs a little way, slows, stops entirely, reverses for a while, and then resumes its climb. A sunrise that goes backwards partway through, and then thinks better of it. Over the following weeks, the ground beneath you climbs through 300, 400, and finally to something in the region of 430 degrees Celsius, hot enough to melt lead and tin and to soften zinc. Your shadow, all this time, has an edge like cut paper, because there is no atmosphere to scatter light into it. The transition from unbearable heat to unbearable dark happens across a boundary you could step over, and the whole cycle, sunrise to sunrise, takes 176 Earth days. 2 full Mercury years pass in a single Mercury day. That is the world. 6 months of daylight, 6 months of night, a temperature range of over 600 degrees between them, and a solar flux 7 to 11 times what falls on Earth, varying as the planet swings around its lopsided orbit. There is an odd tenderness in the fact that Messenger's orbit was deliberately made very lopsided too, dipping to a couple of 100 kilometers above the surface at closest approach, and then retreating out to 15,000 kilometers at the far end. Part of the reason was science. Part of the reason was simply that the spacecraft needed to get away from the planet regularly, because the heat radiating up off that dayside surface would have cooked it if it had loitered. And in among all of this, Mercury has been keeping secrets that make no sense for a world of its size. It has a magnetic field, a real, internally generated one, at about 1% of Earth's strength, discovered by Mariner 10 back in 1974. Small planets are not supposed to have those. They cool quickly and their cores freeze solid, and a frozen core cannot generate a field. Mercury's core, we now know, occupies about 85% of the planet's radius, a proportion unmatched anywhere else in the solar system, and some part of it is evidently still liquid and still moving after 4,500 million years. Stranger still, Messenger found water ice on the planet closest to the Sun. Not much, and not anywhere you could stand. In craters near the poles whose floors have never once received direct sunlight in the entire history of the solar system, the temperature sits below minus 170 degrees Celsius permanently, and ice has accumulated there and stayed. On a world where the equator reaches 430 degrees, there is ice that has never melted. There is also a scar on that surface that tells you something about how violent this neighborhood used to be. The Caloris Basin is an impact crater about 1,550 kilometers across. You could drop the whole of France into it and have room left over for a second France. What makes it remarkable is not its size, but what sits on the exact opposite side of the planet. Directly antipodal to Caloris, on the far side of Mercury, there is a region geologists have never found a better name for than the weird terrain. A jumbled landscape of hills and grooves and broken ground, unlike anything around it. The leading explanation is that the seismic energy of the Caloris impact travelled through and around the entire planet, and converged at the single point furthest from where it landed, and the ground there was thrown into the air by an event on the other side of the world, and it is worth remembering how recently we saw any of this properly. Mariner 10 flew past Mercury 3 times in 1974 and 1975, and because the planet's rotation kept presenting the same face to the spacecraft at each encounter, it mapped only about 45% of the surface. The rest of Mercury, more than half of an entire planet in our own solar system, was genuinely unseen by anyone until Messenger arrived in 2011. There are people alive today who are middle-aged before anybody knew what most of the closest rocky planet looked like, and the planet is shrinking. Long curved cliffs called Labayette Scarps run across the surface for hundreds of kilometers, and they are what you get when a planet's interior cools and contracts and the crust above it has to buckle to fit. Mercury's radius has come down by as much as 7 kilometers. It is a world that is very slowly getting smaller, so this is the first stop, and already the pattern has started. Mercury does not stop you with heat, though it is hot enough. It does not stop you with cold, though it is cold enough. It stops you with energy, with a simple, unforgiving sum in a mass budget that says the fuel to leave weighs more than anything we know how to land. Every world takes something different. Remember that phrase. We are going to walk it all the way out to Neptune and see whether it survives the journey. Because the next planet on the list is the one that everyone assumes will be easy. It is almost exactly Earth's size. It is the closest planet to us that there is. Its gravity is 90% of what you are feeling right now, and the longest anything we have ever built has survived on its surface is 127 minutes. Venus should have been the easy one. On paper, on every sheet of numbers you could reasonably assemble before actually going there, Venus is the planet we should have colonized first. It is the nearest planet to Earth, coming within about 38 million kilometers of us at closest approach, significantly closer than Mars ever gets. It is 95% of Earth's diameter and 82% of Earth's mass, which makes it the only world in the solar system that is genuinely our size, rather than a sculled model of us. Its surface gravity is 8.87 meters per second squared, about 90% of what you're sitting in right now, which means a human skeleton would experience something close to a normal load. It has a thick atmosphere, so there is something to aerobrake against on arrival, that free-braking Mercury refused to give us. It is closer, it is bigger, it is easier to get to, and for a long stretch of the 20th century, a great many serious people assumed that underneath its permanent cloud deck there was something like a warm, wet, primeval version of Earth. There is not. What is under the clouds of Venus is the clearest single demonstration in the solar system that a place can be entirely reachable and still be entirely unusable. Start with the pressure. At the surface of Venus, atmospheric pressure is about 92 bars, 92 times what is pressing on your skin at this moment. To feel that on Earth you would have to descend to roughly 900 meters below the surface of the ocean, which is deeper than all but a handful of crude submersibles have ever gone. And it is not water doing the pressing. It is air, carbon dioxide, 96.5% of the atmosphere, compressed so hard near the ground that it stops behaving like a gas at all and becomes a supercritical fluid, something with the density of a liquid and the freedom of a gas that flows around obstacles and pours into gaps. Then the temperature. 464 degrees Celsius at the surface, more or less everywhere, day and night, equator and poles. That is hotter than Mercury's day side, on a planet nearly twice as far from the Sun, and the reason is the atmosphere. All that carbon dioxide traps infrared radiation so effectively that the heat simply cannot get out again, and the planet has been cooking in its own exhaust for a very long time. 464 degrees is above the melting point of lead, of tin, of zinc. It is a temperature at which rock glows faintly in the infrared, and at which the ordinary electronics that fly on every other mission we have ever launched cease to function within minutes. And then, floating above all of that, the clouds, which are not water. They are droplets of sulfuric acid, suspended in a deck between roughly 48 and 68 kilometers altitude, thick enough to hide the entire surface from optical telescopes for the whole of human history. The upper atmosphere super-rotates, sweeping right around the planet in about 4 Earth days, while the solid body of Venus underneath turns once every 243 days. And it turns backwards. Venus rotates retrograde, the opposite way to almost everything else in the solar system, so that on Venus the sun rises in the west. A day on Venus is longer than a year on Venus. The planet completes an orbit in 225 days, and a rotation in 243. So what happens when you actually go? We know, because the Soviet Union went, repeatedly and stubbornly across 2 decades, and paid for the knowledge with a long line of destroyed spacecraft. Venera 7 returned the first data ever transmitted from the surface of another planet in December 1970, and lasted about 23 minutes. Others followed and did a little better, and then on the 1st of March, 1982, a descent craft called Venera 13 touched down on a plain of flat orange-brown rock and did something nobody had planned for. Picture it. The craft has been falling for the better part of an hour, and for the last part of the descent it has released its parachute entirely, because the air is so thick down here that the vehicle can simply sink through it under its own weight, with a small drag ring to slow it. It settles onto the surface. Around it the light is extraordinary, dim, yellow-orange and completely sourceless, because the cloud deck 50 kilometers overhead diffuses the sunlight so thoroughly that nothing on the ground casts a shadow. There is no sun visible. There is no sky as you would recognize it. There is a horizon, and it is close, and the ground running up to it is covered in flat slabs of rock, like broken paving stones with loose dark soil between them. The pressure is bearing down on every centimetre of the hull. The temperature is at 464 degrees and climbing through the insulation toward the electronics inside. The camera begins to turn, taking the first colour photographs ever made on the surface of another planet, and a small arm extends and drills into the soil to measure what it is made of. All of this is happening inside a machine that is being actively destroyed the entire time it works. It was designed to survive 32 minutes. It survived 127. Then the signal stopped, and that plain of orange rock has been sitting there ever since, in the same light, at the same temperature, unvisited. That was more than 4 decades ago. 127 minutes is still the record. Nothing built by human beings has ever lasted longer on the surface of Venus, and nothing has been back to try. there is a small detail from the follow-up mission that I find genuinely endearing in a bleak sort of way. Venera 14 landed a few days later carrying an instrument designed to press into the soil and measure how compressible it was. The lander ejected its camera lens cap as designed, and the lens cap landed in exactly the spot where the soil arm came down. The most expensive soil mechanics measurement ever attempted on Venus was a measurement of a lens cap. We did eventually get a proper look at the surface, though not with a camera. Between 1990 and 1994, the Magellan orbiter mapped almost the entire planet by radar, seeing straight through the clouds, and what came back raised a question nobody has answered since. The surface of Venus has remarkably few impact craters, and the ones it does have are distributed almost randomly rather than clustering into older and younger regions. On any normal planet, some terrain is ancient and heavily cratered, and some is young and smooth, and you can read the planet's history in the difference. On Venus, everything reads as roughly the same age, a few 100 million years, as though something resurfaced the entire world at once, geologically recently, and erased everything that came before. What that something was, whether it was a global volcanic overturn or something stranger, is still an open argument. Venus also has no magnetic field of its own. What it has is an induced one, generated by the solar wind pushing against its upper atmosphere, and the difference matters more than it sounds. I want to be careful here, because there is a version of this story that treats the heat and the pressure as the whole problem, and they are not. Heat and pressure are engineering problems, and engineering problems have solutions if you're willing to pay. You can build a vessel that survives 92 bars. We build those for the deep ocean. You can build electronics that run at 464 degrees. There is genuine research into silicon carbide circuits that would do exactly that. Landing on Venus and surviving for a long time is difficult, but it is not the wall. The wall at Venus is duration, and it is a wall because of what a return journey requires. To bring a crew home from the surface of Venus, you do not just need people who survive. You need a rocket that survives, a fully fueled ascent vehicle that has to sit on that surface, intact, its tanks uncompromised, its propellant not boiling, its valves and seals and avionics all functional, for however long the mission lasts. Not 127 minutes, weeks, months. And then it has to work, first time, and it has to fight its way up through the densest planetary atmosphere in the inner solar system, which means the thing that gave you free braking on the way in charges you for it on the way out, with interest. Arrival is cheap, departure is not. On Venus, that sentence has teeth, because the atmosphere that helps you arrive is the same atmosphere that crushes what you need to leave, which is why the one architecture for Venus that actually survives serious analysis is the one that never touches the ground at all. Go up to 50 or 55 kilometers into the cloud layer, and something remarkable happens to the numbers. The pressure there is close to 1 bar. The pressure in the room you are in. The temperature is somewhere in the range of 20 to 50 degrees Celsius. It is, in those two variables, the most Earth-like environment anywhere in the solar system outside Earth itself. And because the atmosphere is carbon dioxide, ordinary breathable air is a lifting gas there. A balloon filled with nothing more exotic than the air in your lungs would float in the Venusian sky, the way a helium balloon floats in ours. So the most habitable real estate in the solar system beyond our own planet is a layer of sulfuric acid haze, 50 kilometers above a surface that destroys everything sent to it, and the only reason you could live there is that you would never, ever go down. Every world takes something different. Mercury took energy. Venus takes time. It gives you 2 hours and 7 minutes, and then it takes the machine apart. The next world along has been mapped, driven on, drilled, photographed and studied more thoroughly than anywhere else off Earth, and it is the only planet where the question of a human return is not a thought experiment, but an actual engineering program with budgets and schedules attached, which makes what fails there considerably more uncomfortable. There is a phrase that the engineers who land things on Mars use among themselves, and it has leaked out into the wider world because it is too good not to repeat. They call it the 7 minutes of terror. Here is what it describes. A vehicle arrives at Mars travelling at something like 20,000 kilometers per hour. Roughly 7 minutes later, it is either sitting intact on the surface or it is a crater. In between, it must shed almost all of that velocity by flying into an atmosphere, deploy a parachute at supersonic speed, discard a heat shield, find the ground with radar, and then fire rockets to bring itself the last part of the way down, a sequence of dozens of separate events, each of which must happen in the right order at the right moment, and any one of which will kill the mission if it does not. And it does all of this alone. Not because we do not want to help, but because we cannot. The one-way light travel time between Earth and Mars ranges from about 3 minutes, when the two planets are closest, to about 22 minutes, when they are on opposite sides of the Sun. By the time the first radio signal announcing that the spacecraft has touched the top of the atmosphere reaches a control room on Earth, the entire landing is already over. It has succeeded or failed. Everyone in that room is watching a recording of something that has already happened, and there is not one thing anybody can do about it. The engineers speak into the void anyway. They call out the milestones as the delayed data arrives, and they applaud events that occurred a quarter of an hour ago on another planet. That is what arriving at Mars is like, and it is worth sitting with for a moment, because it is the first time on this journey that the distance has stopped being an abstraction and turned into something you can feel. Mars is close enough that we go there regularly. Mars is also far enough that nobody at home can help you land. So what are we landing on? Mars is a small world, about half Earth's diameter, with a surface gravity of 3.72 meters per second squared, 38% of ours. That number sounds pleasant until you remember that no human being has ever spent more than a few days in any gravity between 0 and 1, and nobody has the faintest idea what a year and a half at 38% does to a skeleton. The atmosphere is a strange in-between thing that manages to combine the disadvantages of having one and not having one. Average surface pressure is about 6.1 millibars, roughly 0.6% of Earth's. It is about 95% carbon dioxide. It is thick enough that a spacecraft arriving at 20,000 kilometers per hour will burn up without a heat shield, and thin enough that a parachute alone can never slow you to a survivable speed. Every Mars landing that has ever worked has been a hybrid of all three techniques: aeroshell, then parachute, then rockets. And even with all of that, the largest mass anyone has successfully put on the Martian surface is around 1 ton. 1 ton. For comparison, a habitat capable of keeping a crew alive for 500 days, plus their supplies, plus the vehicle that has to bring them home, runs to tens of tons. Temperatures are cold, but not spectacularly so by solar system standards. Around 20 degrees Celsius at the equator at noon in summer, down to about minus 125 at the winter poles, with a global average somewhere near minus 63. You would need a heated suit. You would not need a miracle. The landscape itself is on a scale that Earth simply does not offer. Olympus Mons rises about 22 kilometers above the surrounding datum, which is roughly 2.5 times the height of Everest above sea level, and its base is about 600 kilometers across. That combination produces something genuinely strange. The mountain is so wide relative to its height that its slopes average only a few degrees, and a person standing on the flank of the tallest volcano in the solar system would be unable to perceive that they were on a mountain at all. The summit would be below the horizon. You would simply be walking on very slightly tilted ground for days. Valles Marineris runs more than 4,000 kilometers across the planet's face and reaches 7 kilometers deep in places. Laid over North America, it would stretch from one coast to the other, and Mars is a small world, a canyon that long wraps around a significant fraction of its circumference. There is one more thing about this planet worth knowing before we talk about leaving it, and it explains a great deal about the radiation numbers we will come back to later tonight. Mars used to have a global magnetic field, and about 4,000 million years ago it lost it. We know because the ancient crust in the southern highlands is magnetized in stripes, frozen in place, a fossil imprint of a field that was there when the rock cooled and is not there now. Without that field, the solar wind has been stripping the Martian atmosphere away for 4,000 million years, and the surface receives roughly 0.7 millisieverts of radiation per day. That is far less than deep space, because the bulk of the planet blocks half the sky. It is still something in the region of 40 to 50 times the average dose you're receiving where you sit. And then there is the dust, which is the part of Mars that nobody put in the films, and which I have come to think is the most honest thing about the place. Martian dust is very fine, much of it in the low micron range, finer than talcum powder, fine enough to hang in the thin air for weeks. It is electrostatically charged, so it does not settle and stay settled. It clings. Apollo astronauts came back from the moon and reported that lunar dust got into everything within hours, into seals, into hinges, into the weave of the suits, into their lungs, into their eyes. It smelled, they said, like spent gunpowder. Mars has the same problem, with an added complication the Moon does not have, which is weather. Mars has wind. Mars has dust devils and regional storms, and every few Martian years it has a global dust storm that wraps the entire planet in a haze that can persist for months. In 2018, one of those global storms ended the Opportunity rover. Opportunity had been driving on Mars for 15 years on a mission originally planned to last 90 days. The storm blocked so much sunlight that its solar panels could no longer keep it warm, and it went quiet, and it never woke up. A planet-wide weather event killed a spacecraft that had survived everything else Mars had for a decade and a half. But the dust is not the worst thing in the soil. In 2008, the Phoenix lander scooped up Martian regolith near the North Pole and analysed it, and found perchlorate salts at roughly 0.5% to 1% by weight. Perchlorates are not exotic. They are used on Earth in rocket propellant and in fireworks. What they do in a human body is interfere with the thyroid gland's ability to take up iodine, and chronic exposure suppresses thyroid function. Now put those two facts together, because separately they are chemistry footnotes, and together they are a mission design problem. The soil contains a thyroid-disrupting salt. The soil is a fine, clinging electrostatic powder that will be carried into the airlock on every boot and every glove and every fold of every suit, on every single excursion, for 500 days. There is no version of a Mars surface mission where the habitat does not slowly fill with the planet. This is the moment where Mars stops being an adventure and becomes housekeeping, and I think that is genuinely the most unsettling thing about it. We are used to the dangers of space being enormous: radiation, vacuum, cold, velocity. The thing that may actually determine whether people can live on Mars is whether we can keep the dust out of the room, and that is a problem of vacuum seals and vestibules and filter changes and laundry. It is the danger of an ordinary Tuesday, repeated for a year and a half, at a distance from which nobody can send you a replacement filter, and you look up and the sky's not black and it is not blue. It is a pale butterscotch colour, because the suspended dust scatters light in a way ours does not, and at sunset the effect inverts, and the sky immediately around the setting, sun turns cold blue while the rest stays warm. It is genuinely beautiful. It is beautiful in the way that a thing which does not care about you at all can be beautiful. We have arrived. That is the easy half, and it took us 7 minutes and about half a century of trying. Now comes the question this whole video keeps circling back to, and on Mars it has a very specific and very uncomfortable answer, because leaving Mars requires a machine that does not exist, has never existed, and will have to work the first time it is switched on with people inside it. Only one crewed vehicle in the entire history of our species has ever launched from the surface of another world. It was the ascent stage of the Apollo lunar module, and it did it 6 times, and every time it worked. It is one of the great quiet achievements of engineering, and it is worth understanding exactly what it had going for it, because Mars takes almost all of it away. The lunar module ascent stage needed to produce about 1.85 kilometers per second of velocity change to get 2 people from the surface of the Moon into lunar orbit. It did that with a single engine of deliberately brutal simplicity, hypergolic propellants, which ignite on contact with each other and therefore need no ignition system at all, fed by pressurized helium rather than by pumps, because pumps have moving parts and moving parts fail. There was no backup engine. There was no abort mode. There was one engine, and it had to light, and it did. It also had a very short wait. From the moment the lunar module touched down to the moment it lifted off again was, at the longest, about 3 days. Now transpose that to Mars. A Mars ascent vehicle needs roughly 4 kilometers per second to reach low Mars orbit, more than twice the delta V, from a planet with more than twice the surface gravity, through an atmosphere that, thin as it is, still produces meaningful drag on the way up. And because of the exponential in the rocket equation we talked about at the start, twice the delta V does not mean twice the vehicle. It means a great deal more than twice the vehicle, and then there is the weight. A crewed mission to Mars is not a 3-day visit. Earth and Mars return to the same relative positions in their orbits every 25.6 months, and the windows for a low-energy transfer between them open and close on that schedule. A conjunction-class mission, the standard architecture, the one that minimizes propellant, looks like this: 6 to 9 months of transit out, roughly 500 days on the surface, 6 to 9 months of transit home, 2.5 to 3 years total. And here is the part that matters. The departure date is not set by the crew. It is not set by mission control. It is not set by whether the vehicle is ready or whether anyone is well. It is set by orbital mechanics, and orbital mechanics will not negotiate. If you miss the window, the next one is more than 2 years away, so the ascent vehicle has to be there, on the surface, waiting. In most architectures it is sent ahead, landed years before the crew ever leaves Earth, so that its arrival and its readiness can be confirmed before anyone commits, which means that rocket sits on Mars, alone, through dust storms and daily thermal swings of 100 degrees and the slow accumulation of that clinging electrostatic powder in every joint and seal for years. And then a crew arrives and lives beside it for 500 days. I want to stay in that image for a moment because it is the most human thing in this entire video, and it does not involve a single equation. Somewhere on Mars, out of the habitat window, there is a rocket. It is the only way home. It has been sitting in the weather since before anyone left Earth. It cannot be tested, not really. You cannot fire it to check, because it fires once, and there is only one of it, and every gram of its propellant is accounted for. It cannot be replaced. There is no second one, because a second one would cost another launch window and another 2 years. Every morning for a year and a half, the crew get up and look at it. They can walk over and put a hand on it. They will service it, inspect it, brush the dust off it, and they will never know whether it works until the day their lives depend on it working. There has never been anything in the history of exploration quite like that. A single object sitting in plain sight, holding the whole of your future that you are forbidden by physics from testing. Every ship that ever left a harbour could be sailed a little way and brought back. This one cannot. That is the weight of the Mars return problem, and it is not really a number. It is a room with a window in it, and the Apollo comparison, which is the only precedent we have, does not comfort as much as it first appears. Those crews knew that if the ascent engine failed, they would have between a few hours and a couple of days of consumables, and that everybody on Earth would be listening. The distance was close enough that the failure would have been a shared, witnessed event in near real time. On Mars, the light delay means that even the failure arrives late. A crew that cannot leave would send the message, and the people who loved them would learn about it somewhere between 3 and 22 minutes after there was nothing left to decide. The numbers, though, are also worth having, because they are startling in their own quiet way. Nobody seriously proposes carrying the ascent propellant from Earth. The mass does not close. Instead, essentially every credible architecture assumes that the propellant will be manufactured on Mars out of what is already there: the carbon dioxide in the atmosphere, and in some designs, water from the subsurface ice. This is called in situ resource utilization, and it is elegant, and it is the difference between a mission that is merely enormous and one that is impossible. We have tested it exactly once, and only the oxidizer half of it. Perseverance carried a small instrument called MOXIE, a toaster-sized box that pulled carbon dioxide from the Martian air, heated it, and split the oxygen off. It ran 16 times between 2021 and September 2023. At its best, it produced about 12 grams of oxygen per hour. Over its entire operating life, it made 122 grams. 122 grams. That is roughly 4 hours of breathing for one person. A crewed Mars ascent vehicle needs somewhere between 25 and 30 tons of liquid oxygen. Sit with the ratio for a second, because I think it is the single most clarifying number in this whole part of the story. The gap between what we have demonstrated and what we require is a factor of something like 200,000. That is not a criticism of MOXIE, which did exactly what it was built to do, and did it beautifully. It proved the chemistry works in the real Martian environment, at the real temperatures, with the real dust in the real air, which is the thing you cannot prove in a laboratory. But it is a very sober measure of where we actually are. We have proved the principle. We have not built anything that could keep a crew alive, and the thing we have not built is the thing that brings them home. It is worth saying, because it would be unfair not to, that Mars has also given us the clearest evidence in decades that hard things on other planets are sometimes easier than we feared. Perseverance carried a second small experiment, a helicopter called Ingenuity, weighing under 2 kilograms, designed to prove that powered flight was possible in an atmosphere 1% as dense as Earth's. The engineering consensus beforehand was cautious. Rotor blades in air that thin have almost nothing to push against. The machine had to spin them at more than 2,000 revolutions per minute simply to stay up. It was given 5 flights as a technology demonstration. It flew 72 times over nearly 3 years and became the first aircraft to operate on another world, and it only stopped because a rotor blade was damaged on a landing in rough terrain. That is the counterweight to everything else in this part of the story. Sometimes the thing everybody expected to be impossible turns out to be merely difficult, and then it flies for 3 years. But an ascent vehicle is not a 2-kilogram helicopter, and here is the difference that matters. Ingenuity was allowed to fail. It was a demonstration. If it had crashed on Flight 1, the mission would have continued and everyone would have learned something. There is no version of a crewed ascent vehicle that is allowed to fail, and no version of it that gets 72 attempts. It gets 1. And unlike almost every other piece of high-risk aerospace hardware ever built, it cannot be flown in a rehearsal, because rehearsing it consumes it. Arrival is cheap, departure is not. On Mercury, that sentence was about propellant. On Venus, it was about heat and time. Here it stops being about physics at all and becomes about a machine that nobody has made yet, sitting in a place where nobody can go and fix it. And there is something else about this world that we'll need much later tonight, so let me plant it now rather than argue it. Every difficulty I have just described is a difficulty about hardware. Tanks, engines, seals, filters, oxygen. All of it, in principle, buildable. None of it a law of nature. If Mars were only a hardware problem, we would already have a date. Mars is not only a hardware problem. There is a second problem, and it is riding in the crew compartment, and it has been quietly accumulating since the day the vehicle left Earth. We are going to come back to it, and when we do, everything we have said tonight is going to shift about 10 degrees to the left. For now, though, we leave the ascent vehicle standing in the dust and we keep going outward, because the next stretch of the journey is the one where the solar system stops being a set of destinations and starts being a distance. Ahead of us is a region that films have taught us to fear for entirely the wrong reason. Everything you have ever seen on a screen about the asteroid belt is wrong, and it is wrong in a way that is worth correcting carefully, because the truth is stranger and considerably more frightening than the fiction. The fiction is a debris field. Rocks tumbling past the cockpit window, the pilot jinking left and right, the odds of successfully navigating it quoted at something absurd. The reality is that the main belt, which occupies the region between roughly 2 1/10 and 3 3/10 times Earth's distance from the Sun, contains well over 1 million objects larger than a kilometre across. And if you added every one of them together, all the asteroids in the belt, the combined mass would come to about 4% of the mass of the Moon. Ceres alone, the largest of them, accounts for something like 1/4 of the total. Everything else in that entire vast annulus, all million-plus objects, shares the remaining 3/4. Spread that little mass through a volume that large, and the numbers become absurd in the other direction. The average separation between belt objects of any appreciable size is on the order of 1 million kilometres. That is more than twice the distance from here to the Moon. If you were standing on a typical asteroid, you would not be able to see another one as anything other than a point of light indistinguishable from a star. Every spacecraft we have ever sent through the belt has crossed without incident. Pioneer 10 and 11, both Voyagers, Galileo, Ulysses, Cassini, New Horizons, Juno. Mission planners do not regard the crossing as a significant hazard, and they never really have. The rocks are not the problem. The problem is what the belt actually is, which is the place where the journey stops being a trip. Up to this point, everything we have discussed has been measured in months. Mars is 6 to 9 months away. Venus is a matter of months. Even Mercury, expensive as it is in energy, is a place a fast trajectory could reach in a year or so if you were willing to arrive too quickly to stop. Cross the belt and the units change. A low-energy transfer from Earth to Jupiter takes about 2 years and 9 months, one way. To Saturn, it's around 6 years, one way. You're no longer packing for a journey. You're designing a way of living in a sealed volume for longer than most people stay in a job, and something else changes as you cross, and it changes silently. The sun starts going out, sunlight falls off with the square of distance. At Earth, the solar flux is about 1,361 watts per square metre, a bit over a kilowatt on every square metre of ground, which is why solar panels work here at all. At Jupiter, it is around 50 watts per square metre, about 3 7/10% of what we get. At Saturn, it is around 15, about 1%. At Neptune, it is around 1.5 watts per square metre, roughly 1/900th of what falls on your garden. Juno, which has been orbiting Jupiter since 2016, flies the largest solar arrays ever sent into deep space, 3 wings totaling something like 60 square meters of cells. That is roughly the floor area of a small flat, unfolded in space, pointed at the Sun. At Jupiter it produces on the order of 500 watts, 60 square meters of the best photovoltaic technology our civilization can build, and it generates less power than the kettle in your kitchen. That single comparison tells you why every mission to the outer solar system beyond Jupiter runs on nuclear power instead. Plutonium heat converted directly to electricity, because past a certain radius the Sun is no longer a power source, it is just the brightest star. Let me stop here, because we are roughly halfway, and I want to put the pieces on the table and look at them together before we go any further out, since from here the worlds get stranger, and it is easy to lose the thread among the wonders. We have visited 3 planets. At each one we arrived without much difficulty, and at each one the return journey failed, and it failed differently every time. At Mercury, the return failed on energy. The planet sits deep in the Sun's gravity well with no atmosphere to brake against, and not enough mass to help, so every kilometre per second that 6.5 years of gravity assist carefully removed has to be paid back in propellant that nobody knows how to land there. At Venus, the return failed on duration, not on heat as such, and not on pressure as such, but on how long anything survives in them. The record is 127 minutes set in 1982, and a crude ascent vehicle would need to hold together for months. At Mars, the return failed on a machine. Everything else about Mars is soluble, and much of it is nearly solved. What is not solved is the one object that has to lift people off the surface, has never been built, has to sit alone in the weather for years, and gets 1 attempt. 3 worlds, 3 failures, and no obvious relationship between them. Energy, duration, hardware. They do not look like the same problem. They do not even look like the same category of problem. One is physics, one is materials science, one is engineering program management. Keep that in your mind as we cross the belt, because we have 5 worlds left and the failures are about to get considerably stranger, and somewhere out past Saturn the pattern is going to start showing through. Before we go, the belt deserves a moment of its own, because there are real places in it, and they are not just rubble. Ceres is 940 kilometers across, round under its own gravity, and is the only dwarf planet in the inner solar system. When the Dawn spacecraft arrived, it found bright deposits in a crater called a crater that turned out to be sodium carbonate, salts, left behind by briny water that reached the surface from a reservoir below and evaporated away into vacuum. There is liquid, or there was recently, inside an object in the asteroid belt. Vesta, the second largest, has an impact basin 500 kilometers wide at its south pole, which on a body only about 525 kilometers across means the crater is very nearly the size of the world it is on. The debris from that impact is still arriving. There is a recognized class of meteorites found on Earth that we can trace directly back to Vesta, and there is Psyche, an object rich enough in metal that one serious hypothesis holds it to be the exposed core of a protoplanet that was shattered early in the solar system's history, the naked iron heart of a world that never finished forming. A spacecraft launched toward it in 2023 and will arrive in 2029. The belt also carries a fingerprint of Jupiter's power. If you plot how many asteroids orbit at each distance from the Sun, the distribution is not smooth. There are gaps, the Kirkwood gaps, swept almost clean. They sit at orbital periods that are simple fractions of Jupiter's, so that an object there receives a gravitational nudge from Jupiter at the same point in its orbit again and again, and over millions of years those nudges accumulate until the object is thrown somewhere else. Jupiter is also the reason the belt never assembled into a planet at all. Its gravity kept the relative velocities of the material there too high for anything to stick together. There should be a world here. Jupiter would not allow one. There is something worth noticing in that. We have crossed a region that everybody imagines as crowded and found it almost entirely empty, and we have found that the danger here is not the thing you can see. The belt does not threaten a crew with collision. It threatens them with duration, with the slow arithmetic of supplies and spare parts, and a sun that is dimming behind them, and with the fact that from about here onward, nobody is coming to get you. That is a pattern I would like you to keep half an eye on, because it is going to repeat, and the next time it does, it will be considerably harder to ignore. Which is a fitting introduction, because Jupiter is next, and Jupiter does not permit a great many things. Jupiter has 318 times the mass of Earth and 11 times its diameter. If you took every other planet in the solar system, Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, and rolled them into a single ball, Jupiter would still be more than twice as heavy as all of them put together. It is not the largest planet in a list of planets. It is, apart from the Sun, essentially the solar system, and everything else is detail, and you cannot land on it. Not because the surface is hostile, because there is no surface. This is a sentence people repeat without quite believing, so let us do it properly. Imagine descending into Jupiter. You enter the upper atmosphere, which is about 90% hydrogen and 10% helium by number of molecules, and you fall. The pressure rises, the temperature rises, you pass through ammonia clouds, then ammonium hydrosulfide, then water clouds, and the pressure keeps rising. At some depth, the hydrogen around you becomes dense enough that calling it a gas stops meaning anything. It grades continuously into a hot, dark, compressed fluid, with no boundary you could point at, no shoreline, no moment where you could say the air ended and the ocean began. Keep going and the pressure becomes so extreme that hydrogen is squeezed into a metallic state, a liquid that conducts electricity like a metal, and it is the churning of that layer that generates the planet's magnetic field. There may be a rocky or icy core somewhere in the middle, partially dissolved into the fluid above it. Nobody knows, and nothing will ever go and look. We have tried once. In December 1995, the Galileo mission released an atmospheric probe into Jupiter. It transmitted for 58 minutes, descending about 156 kilometers into the atmosphere, reaching around 23 bars of pressure and 153 degrees Celsius before it stopped. 58 minutes to fall 156 kilometers into a planet 140,000 kilometers across, and it never reached anything remotely like a floor because there is not one to reach. So the honest version of visiting Jupiter is visiting its moons, and there are wonderful ones. Ganymede is larger than Mercury and is the only moon in the solar system with a magnetic field of its own. Callisto is one of the most heavily cratered objects known, a preserved record of the early solar system. Europa has a smooth shell of water ice, with an ocean beneath it that probably contains more liquid water than every ocean on Earth combined, and it is one of the best candidates anywhere for life beyond our own world, and you cannot stay at any of them because of something you would never see coming. Jupiter's magnetic field is not merely strong. Its trapped particle radiation is roughly 20,000 times more intense than the Van Allen belts around Earth, and about 1,000 times more intense than Saturn's. Outside the Sun itself, it is the most severe radiation environment in the solar system. What feeds it is genuinely extraordinary, and it is worth following the chain, because it connects two things that look unrelated. Io, the innermost of the four large moons, is squeezed and released by Jupiter's gravity on every orbit, and by the gravity of Europa and Ganymede pulling it out of a circular path so that the whole moon flexes like a stress ball. That flexing heats it, and Io is consequently the most volcanically active body in the solar system, with more than 400 active volcanoes throwing material off the surface continuously. Roughly a ton of sulfur and oxygen per second escapes Io's gravity entirely, and forms a donut of gas around Jupiter along Io's orbital path, the Io plasma torus. Jupiter's magnetic field grabs that gas, strips electrons off it, and whips the resulting charged particles around with the planet's rotation, which takes less than 10 hours. That whipping accelerates them to relativistic energies. Io's volcanoes are, in a very direct sense, loading the gun. Now put a spacecraft into that. Juno, which has been orbiting since July 2016, carries its most sensitive electronics inside a vault made of titanium, with walls about a centimetre thick, weighing something like 200 kilograms. That is not shielding in the sense of a lead apron at the dentist. That is a strongbox, and the spacecraft flies a highly elliptical polar orbit specifically so that it spends as little time as possible in the worst of the belts, swooping in fast, taking its data, and getting out. There is a small irony in its history. A valve problem early on left Juno in a 53-day orbit rather than the 14 days originally planned, and one accidental consequence was a much lower cumulative radiation dose, which is part of why the mission has lasted as long as it has, and Europa Clipper, which launched in October 2024 to study the most interesting moon in the system, does not orbit Europa. Read that again, because when I first understood it, I found it genuinely chilling. The mission designed to study Europa in detail deliberately does not go into orbit around Europa. It orbits Jupiter on a long loop and makes repeated flybys instead, dipping in and retreating over and over. The reason is that sustained orbit at Europa's distance from Jupiter would accumulate a radiation dose that no reasonable shielding could survive. We built a mission architecture around avoiding a place we wanted to be, because the surface of Europa itself receives a dose on the order of several sieverts a day. To put that in a human frame, a whole body dose of around 4 to 5 sieverts, received at once, kills roughly half the people who receive it without intensive medical care. An unshielded person standing on the ice of Europa would receive a lethal dose in something between a day and 2 days. Let me put you there, briefly, because I think this is the moment on our journey where the danger becomes something new. You're aboard a vehicle inbound through the Jovian system. Jupiter fills a quarter of the sky ahead, not a disk you look at, but a wall you're falling toward, banded in cream and rust and ochre, with the whole pattern visibly moving because the planet turns once in under 10 hours and you can watch the band slide. Below you, Io, sulfur yellow, mottled orange and white. No impact craters anywhere because the volcanoes resurface it faster than the craters can accumulate. On the limb, a plume stands up off the edge of the moon, silhouetted, perfectly still to look at, actually rising at a kilometre per second. It is one of the most beautiful sights available anywhere in this solar system, and while you're looking at it, you're dying. There is nothing to feel. No heat, no pressure, no sound, no smell, no sensation of any kind. The particles pass through the hull and through the water in your body, and each one leaves a track of broken molecules and torn strands behind it, and you would have no way of knowing. The instruments that matter are behind a centimetre of titanium. You are not. There is no alarm you could design that would help, because there is nowhere to go. The field is everywhere out here. It does not have an edge you could step outside of, and the only shielding that works is mass, and mass is the one thing you cannot afford after a journey of 2 years and 9 months. And I want to give you a sense of the scale of the thing doing it, because the magnetosphere is not a local feature. If Jupiter's magnetic field were visible from Earth, in the way the moon is visible, it would appear several times wider than the full moon in our sky. A structure so large that a planet 780 million kilometers away would look like a significant object in our night. It streams out behind Jupiter in a tail that reaches most of the way to Saturn's orbit. When we talk about the radiation environment at Jupiter, we're not talking about a hazard zone near the planet. We're talking about a region of the solar system. Jupiter is also quietly still generating its own heat. It radiates about 1 6/10 times as much energy as it receives from the Sun, left over from its formation, and from the fact that it is still very slowly contracting under its own gravity. It is not a star and never was one. You would need something like 80 times its mass to squeeze hydrogen into fusion. But it is warm from the inside in a way that Earth is not, and it always has been. And it has weather that outlives civilizations. The Great Red Spot is a storm that has been observed continuously for at least 190 years, and there are observations from the 1660s that may well be the same feature, in which case it has been turning for longer than the United States has existed. It is currently shrinking. It used to be 2 or 3 Earth diameters across. It is now roughly 1. Something is happening to it, and nobody knows what, and it may close entirely within the lifetime of people watching this. Then there is the arithmetic of simply being there and coming back. A chemical propulsion round trip to the Jovian system, out and back, is on the order of a decade before you spend a single day doing anything useful when you arrive. Add operations at the moons, and you are looking at something between 11 and 15 years for one mission. And every day of that out at Jupiter is a day inside the field. That is the wall at Jupiter, and it is unlike everything before it. Mercury's wall was arithmetic. Venus's wall was a clock. Mars's wall was a machine. Jupiter's wall is invisible, has no location, cannot be sensed, cannot be outrun, and does not care in the slightest what you have built. Every world takes something different. So far the phrase is holding perfectly, which brings us to the world that everybody wants to see, the one that shows up on the covers of the books, the one with the rings. And I have to tell you that of everything out here, Saturn is the cruelest, because it offers something that looks very much like a welcome. Saturn contains 95 times the mass of Earth inside a body, more than 9 times Earth's diameter, and if you work out what that means for its density, you get a number that people assume must be a misprint. Saturn's average density is about 0.69 grams per cubic centimetre. Water is 1. Saturn is less dense than water. If you could find an ocean large enough, the second largest planet in the solar system would float in it. Like Jupiter, it has no surface, so everything we said about descending into Jupiter applies here with the numbers adjusted. There is nothing to land on, nothing to stand on, and no depth at which a vehicle could rest. What it has instead are the rings, and the rings are worth being precise about, because the precision is where the strangeness lives. The main ring system spans roughly 280,000 kilometres from inner edge to outer edge, more than 2/3 of the distance from the Earth to the Moon, and the average thickness of that structure is somewhere between about 10 and 30 metres. 10 metres. If you scaled the rings down so that they were the width of a football pitch, they would be very much thinner than a sheet of paper. They are made almost entirely of water ice, in pieces ranging from grains of dust up to boulders the size of a house, all of them orbiting independently, each one on its own path, sorted by the mathematics of orbital resonance into bands and gaps and waves. Cassini is our witness here. It arrived in July 2004 and worked for 13 years, and I think it is the most complete exploration of another world we have ever performed. It mapped the rings, flew through the plumes of Enceladus and tasted them, watched storms wrap around the northern hemisphere, and tracked the seasons of an entire Saturnian year segment. It found things nobody expected. Enceladus, a moon only about 500 kilometres across, vents water vapour, salt and organic molecules from cracks near its south pole, and Cassini flew directly through those plumes and sampled them, detecting molecular hydrogen, which is a signature of ongoing chemical reactions between water and rock beneath the ice. There is a hydrothermal system running inside a moon that could sit comfortably inside the country you live in. It found the hexagon. At Saturn's north pole there is a jet stream that flows in a six-sided path, a genuine persistent hexagon roughly 30,000 kilometres across, present since at least the Voyager encounters in 1980 and 81, sharp-cornered, with clouds moving along its straight edges. It is not an artifact and it is not a coincidence, and the physics that produces it is broadly understood in the laboratory, and it is still one of the most unlikely-looking things in the solar system. It also found that the rings are temporary. Material is falling from them into Saturn's atmosphere as what researchers have called ring rain, at a rate high enough that the whole system may be young, possibly only 100 to 400 million years old, and may not last much longer, which would mean that the rings did not exist when anything interesting was happening on Earth's surface, and will be gone again, and we happen to be alive during the brief window in which the most photographed object in the sky exists at all. And at the end, on the 15th of September 2017, Cassini was deliberately flown into Saturn and destroyed. Not because it had failed, it was still working, but because it was running out of propellant, and an uncontrolled spacecraft in the Saturn system might eventually have struck Enceladus or Titan and contaminated a possible biosphere with terrestrial bacteria. The final phase, which they called the grand finale, was 22 orbits threading the 2,000-kilometre gap between the innermost ring and the cloud tops, going where nothing had ever been because there was no longer any reason to be careful. Then it turned its antenna toward Earth and transmitted for as long as it could as it burned. But the thing I actually want to talk about at Saturn is a moon, because Titan is the most disorienting place in this entire solar system, and it is disorienting for a reason that has nothing to do with how alien it is. On the 14th of January 2005, a European probe called Huygens, which had ridden to Saturn attached to Cassini, detached and descended through Titan's atmosphere. It took about 2.5 hours to come down, photographing as it went, and it landed on a damp, dark plain scattered with rounded cobbles. Rounded, which means something moved them and tumbled them, the way a riverbed rounds stones. It then transmitted from the surface for another 72 minutes, until Cassini set below Titan's horizon and the relay link was lost. 72 minutes. Set that beside Venera 13's 127 minutes on Venus, because between them those two numbers are the entire human record of standing on the surface of a world in the outer or in a solar system that is not Earth or the Moon. 2 machines, 2 afternoons, 40 years apart. Everything else we know about the surfaces of other planets, we know from orbit or from a rover on Mars. Now, what Huygens measured on the ground is the part that unsettles me. Surface temperature, about minus 179 degrees Celsius, which is roughly 94 Kelvin. Surface pressure, about 1.45 bars, 1.45 bars, let that land. The pressure at the surface of Titan is about 45% higher than the pressure in the room you're sitting in. It is well within the range a human body handles without difficulty, comparable to being a few meters underwater or in a slightly overpressurized aircraft cabin. Titan is the only place in the solar system other than Earth where a person could stand outside without a pressure suit and not be harmed by the pressure difference at all. The atmosphere is about 95% nitrogen, which is what most of our own air is, and Titan's gravity is only about 14% of Earth's, and its air is denser than ours. Those two facts together produce something almost unbearable. A human being on Titan, wearing a pair of strapped-on wings, could fly, not glide, fly under their own muscle power by flapping. It is one of the very few places in the universe we know of where an unassisted person could get airborne. So here is a world with breathable pressure and an atmosphere you could fly through, and if you stepped out onto it you would die, and the thing that would kill you is the cold. 94 Kelvin freezes exposed skin in seconds and would destroy your lungs before you had finished the first breath, and there is no oxygen in that breath anyway. Titan needs a heated suit and an oxygen supply. It does not need a pressure vessel. It is simultaneously the most hospitable and the most lethal surface in the outer solar system, and it manages that by being generous in every variable except one. Titan's atmosphere is also enormous in a way that is easy to miss. It extends roughly 600 kilometers above the surface, about 10 times the vertical extent of Earth's, on a body smaller than Mars. From a distance, Titan does not look like a moon with an atmosphere. It looks like a fuzzy orange ball with no features at all, which is exactly what Voyager 1 saw when it flew past in November 1980. And that flyby is worth a moment of its own because of what it cost. Voyager 1 was routed to make a close pass at Titan deliberately, and that trajectory threw it up and out of the plane of the solar system, which meant giving up any possibility of ever visiting Uranus or Neptune. Mission planners traded 2 entire planets for 1 moon, on the reasoning that a world with a thick nitrogen atmosphere was worth more than 2 more gas giants. Then the spacecraft arrived and found a featureless orange haze that its cameras could not see through at all, and here finally is the return problem at Saturn, and it takes a shape we have not met yet. The planet itself is not a destination in any meaningful sense, because there is nothing to leave from. Everything about a Saturn mission therefore happens at the moons, which means the return leg starts from Titan or Enceladus, tiny bodies whose escape velocities are mercifully low. Ascent is genuinely the easy part out here. What is not easy is everything before it. 6 years to arrive on a low-energy trajectory, 6 years back, and in between, a crew must keep an ascent vehicle and its propellant functional at 94 Kelvin, in an atmosphere of methane and nitrogen, powered by a sun delivering 1% of what it gives Earth, with no possibility of resupply for however long they stay. Saturn does not close the door with a wall, it closes it with a calendar. I find something almost dreamlike in the fact that we could not even agree how fast Saturn rotates for most of the space age. On a rocky planet, you time a feature going round. Saturn has no solid surface, and its clouds at different latitudes move at different speeds, and the usual backup, timing the wobble of the magnetic field, failed too, because Saturn's magnetic axis is almost perfectly aligned with its rotation axis, and therefore does not wobble. The answer eventually came from reading waves in the rings themselves, which respond to oscillations deep inside the planet. Saturn turns once in about 10 hours and 33 minutes, and we only established that in the last decade or so. That is Saturn's particular cruelty, and it is why I called it the cruelest world out here. Mercury is honestly hostile. Venus is honestly hostile. Jupiter is honestly hostile. Titan looks like an invitation. There is weather there and rain, methane rain, falling through an orange haze onto a landscape with rivers and lakes and shorelines and seasons. There are dunes. It is the only other place we know of with standing liquid on its surface. Everything about it says come in, and the answer is still no, and the reason is a single number. Every world takes something different. Saturn takes the ground itself, and its best moon takes the heat. Beyond here we leave the part of the solar system that humanity has looked at properly. From this point outward, we have 1 flyby per planet, decades old, and everything we say is built on hours of data taken by a single spacecraft that has since gone dark and cold and left the solar system entirely. On the 24th of January 1986, a spacecraft passed through the Uranian system at about 19 kilometers per second, taking pictures as fast as it could, and then it was gone. That is it. That is the entire close-range human observation of the seventh planet. One afternoon, 40 years ago, everything we know from nearby about a world 4 times Earth's diameter, with rings and 27 known moons and an interior nobody understands, comes from a few hours of data taken by Voyager 2 before it continued on toward Neptune. There has not been another mission. There is no mission currently on its way. If one launched in the early 2030s, as the scientific community has repeatedly asked for, it would arrive in the mid-2040s. I find that genuinely difficult to sit with. There is an entire planet in our own solar system that we have looked at properly once, before most people watching this were born, and we have simply not been back. And it is not a boring planet. It is the strangest of the 8, and the strangeness starts with its orientation. Uranus is tipped over. Its axis of rotation is inclined about 98 degrees, which means it is not so much spinning as rolling along its orbit, lying on its side, with its poles pointing alternately at the Sun. Every other planet spins more or less upright like a top. Uranus is a barrel. The consequence is the most extreme seasonal cycle anywhere. Uranus takes 84 Earth years to go round the Sun, and because of that tilt, each pole spends 42 consecutive Earth years in continuous sunlight, followed by 42 consecutive Earth years in continuous darkness. Not a long winter. A winter longer than most careers. A person born at one pole at the start of a Uranian night would reach retirement age before the Sun came up. When Voyager 2 arrived, it happened to catch the planet near southern summer solstice, which meant the South Pole was pointing almost directly at both the Sun and the spacecraft. What came back was an almost featureless pale blue-green disk, with barely a cloud to be seen, and for a while the assumption was that Uranus simply had no weather. Later observations with better instruments have found storms and bright clouds and seasonal changes, so the blankness was partly an artifact of when we happened to look. We caught the planet on a quiet afternoon and drew conclusions about its entire personality. The colour, incidentally, tells you almost nothing. Uranus looks blue-green because methane in the upper atmosphere absorbs red light and lets blue through. That is a fact about the top few % of the atmosphere. It says nothing whatsoever about what is underneath. What is underneath is not what most people picture. Uranus and Neptune are not gas giants in the way Jupiter and Saturn are. They are ice giants, and the word ice is doing something misleading there. Beneath a hydrogen and helium envelope lies a mantle of water, ammonia and methane. But at those pressures and temperatures it is neither cold nor solid. It is a hot, dense, electrically conducting fluid, thousands of degrees, squeezed to densities that have no everyday equivalent. Astronomers call it ice for historical reasons about where the material formed, not because it is frozen. And something about that layer produces the planet's other great oddity. Uranus has a magnetic field that is tilted about 59 degrees away from its rotation axis and offset from the planet's centre by roughly a third of a planetary radius. Earth's magnetic poles wander a little from the geographic ones. Uranus's field is not merely tilted, it is displaced, so that its strength at the surface varies by a factor of 10 depending on where you are. The leading idea is that the dynamo generating it operates in a relatively thin shell of conducting fluid, rather than deep in a core, which produces messier geometry. But the real mystery at Uranus is a temperature, and it is the kind of anomaly that ought to be much more famous than it is. Uranus holds the record for the coldest temperature ever measured in a planetary atmosphere anywhere in this solar system. About 49 Kelvin, roughly minus 224 degrees Celsius, in the upper troposphere. That is colder than Neptune, which is 1,500 million kilometers further from the Sun. That should not be possible, and the reason it happens is that Uranus appears to have no internal heat. Every other giant planet radiates substantially more energy than it receives from sunlight. Jupiter emits about 1 6/10 times what it absorbs, Saturn about 1 8/10, Neptune about 2 6/10. Uranus emits barely more than it takes in. The leftover warmth of its formation is either gone or is not reaching the surface. Two planets, nearly the same size, nearly the same composition, formed in the same disk around the same star at roughly the same time, and one of them has an engine running and the other does not. The most popular explanation ties it back to the tilt. Whatever hit Uranus hard enough to knock it onto its side early in its history may also have disrupted its interior badly enough to stratify it, leaving layers that cannot convect, so that heat which should be rising to the surface is trapped somewhere below, and has been for 4,000 million years. That is a lovely hypothesis. It is also completely untested, and it will remain untested until somebody sends a probe into that atmosphere, and nobody has scheduled one. The moons are strange too. There are 27 known, named not for Greek and Roman gods like almost everything else in the sky, but for characters from Shakespeare and from Pope: Titania, Oberon, Ariel, Umbriel, Miranda. And Miranda is a genuine oddity, a small moon under 500 kilometers across, whose surface looks as though it was assembled from mismatched pieces, with terrains of wildly different ages jammed against one another. It carries Verona Rupes, a cliff around 20 kilometers high, which is the tallest known cliff anywhere in the solar system. Because Miranda's gravity is so weak, an object dropped from the top of it would take something like 12 minutes to reach the bottom. You could step off the edge and fall and have time to think about it properly. The rings, meanwhile, were found by accident. In 1977, astronomers were watching Uranus pass in front of a distant star, an occultation, a standard technique for measuring a planet's atmosphere. The star blinked out several times before Uranus reached it, and then blinked out several more times after it had passed. Something narrow and dark was orbiting the planet. There are 13 known rings now, and we found them because a star flickered. It is worth remembering how new this planet is to us. Uranus is the first planet in history that had to be discovered, rather than simply being one of the wandering lights that everybody had always known about. William Herschel found it in 1781 with a telescope he had built himself in his own garden, and he initially reported it as a comet, because the idea that there might be another planet had not seriously occurred to anyone. The solar system had 6 planets for the whole of recorded human history, and then one evening in Bath it had 7. And the thin thread we're hanging all of this on is worth stating plainly. Voyager 2 returned its Uranus data across roughly 3,000 million kilometers at about 21.5 kilobits per second, slower than a household modem from the 1990s. Everything humanity knows about the up-close appearance of an entire planet arrived down a link slower than the one people once used to load a single photograph. So what happens if you go? The honest answer is that we do not really know, and that is itself the answer. Uranus is the first world on this journey where the barrier is not a specific physical fact we can name. It is the sheer length of the undertaking. A mission there is a career. Anyone who devotes themselves to it as a young researcher will be near the end of their working life when the data comes home, and any crew that went would spend a substantial fraction of a human lifetime in transit for a single arrival. Every world takes something different. Uranus takes decades, and it takes them from the people who go and from everybody who waits. And the 8th planet, the last one, takes something stranger still, because out there, at 4,500 million kilometers from the Sun, with almost no light and almost no warmth, something is blowing at 2,000 kilometers an hour, and nobody can say what is driving it. Neptune was found with a pencil. That is not quite literally true, but it is close enough to be worth saying, because of all the discoveries in the history of astronomy, it is the one that most clearly demonstrates that mathematics knows things before anybody looks. By the 1840s, Uranus had a problem. It was not where it was supposed to be. Astronomers had been tracking it since Herschel found it, and its observed position kept drifting away from the position that Newton's laws predicted. Not by much, but consistently, and in a way that would not go away. 2 mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently reasoned that something further out was tugging on it, and each of them worked backwards from the size of the discrepancy to calculate where that something had to be. Le Verrier sent his prediction to the Berlin Observatory. Johann Galle pointed a telescope at the specified coordinates on the very first night he tried, in September 1846, and found a planet within a degree of where the arithmetic said it would be. Nobody had ever seen it. Nobody had suspected it existed. It was located by noticing that another planet was very slightly in the wrong place. Neptune orbits at about 4,500 million kilometers from the Sun, and takes 165 Earth years to complete one circuit, which means that in 2011, Neptune finished its first full orbit since the night Galle found it. 1 Neptunian year had passed between its discovery and quite recently. That is the timescale we're working with now. Voyager 2 passed it on the 25th of August 1989, and that flyby is still the only close observation ever made of the 8th planet. The trajectory was deliberately aimed to pass within about 4,950 kilometers of Neptune's north pole, the closest approach of the entire Grand Tour, closer to a planet than the spacecraft had ever been to anything, and the reason was that this bent its path sharply southward and flung it toward the moon that everyone actually wanted to see. Before we get to that moon, though, there is the wind. Neptune has the fastest winds ever measured anywhere in the solar system. Sustained speeds in the equatorial region run around 2,000 kilometers per hour, with the highest measured values close to 2,100. To put that in a human frame, the strongest wind ever recorded on Earth was a gust of about 408 kilometers per hour. Neptune's winds are roughly 5 times that, and they are not gusts. They are the ordinary state of the atmosphere. Now here is why that should not happen. Neptune receives about 1/900th of the sunlight that Earth does, around 1.5 watts per square meter. That is not a lot of energy arriving. On Earth, weather is fundamentally a machine for redistributing solar heat. The sun pours energy into the tropics, the atmosphere moves it toward the poles, and everything we call weather is the machinery of that transfer. The expectation, entirely reasonable, was that as you move away from the sun and the energy input drops, the weather should get quieter, calmer, more sluggish. The opposite happens. The most violent atmosphere in the solar system belongs to the planet that receives almost no light at all. Part of the answer is that Neptune is heated from below rather than above. It radiates about 2 6/10 times as much energy as it absorbs from the sun, drawn from the heat of its own formation, and possibly from ongoing settling and separation in its interior. So there is an engine, there is a source. What nobody can explain is why Neptune has that engine, and Uranus, its near twin in size and composition, does not. 2 planets built from the same material in the same place, and one of them is running hot and screaming and the other is inert. Voyager 2 also photographed a vast dark oval in Neptune's southern hemisphere, roughly the size of Earth, and it was promptly named the Great Dark Spot on the obvious analogy with Jupiter's. When the Hubble Space Telescope looked in 1994, it had gone, completely. New dark spots have appeared since in different places and have faded again. Jupiter's storm has lasted centuries, Neptune's last a few years and vanish. Whatever is happening in that atmosphere is not just faster than Jupiter's, it is less permanent, and nobody knows why either of those things is true. Its rings are odd as well. They are faint, and they are not uniform. The material is bunched into arcs, dense clumps within otherwise thin rings, and by every straightforward calculation those clumps should have spread themselves out into smooth, even rings long ago. They have not. Something is confining them, and the explanations on offer remain partial. And then there is Triton, which I think may be the single strangest large object in the solar system. Triton orbits Neptune backwards. Its motion is retrograde. It goes round the wrong way relative to the planet's rotation. That is not a curiosity. It is close to a proof, because a moon that forms in place, out of the disk of material around a young planet, inherits that disk's direction. It cannot end up going the other way. So Triton did not form there. Triton almost certainly formed out in the Kuiper Belt, as an independent body, and was captured by Neptune at some point. An event that would have been catastrophic, wrecking whatever satellite system Neptune had before and leaving the debris we see today. Its surface temperature is about 38 Kelvin, minus 235 degrees Celsius. That is the coldest directly measured surface anywhere in this solar system, colder than Pluto, colder than anything Voyager or New Horizons or anything else has ever put a thermometer near, and it is geologically active. Let me put you there for a moment, because this is a place I do not think enough people have stood in their imagination. You are on Triton. The ground under your boots is nitrogen frost, pale pink and white, and it does not crunch, because there is no air worth speaking of to carry the sound. Overhead, filling far more sky than the moon fills at home, is Neptune. Deep blue, banded, its clouds moving fast enough to see. The light is extraordinary. It is daytime, technically the sun is up, and it is a point of light no larger than a bright star, and everything around you is lit at about 1/900th of the brightness of a day on Earth. That is dimmer than deep twilight. You could not read by it. Yet it is enough to show you the whole landscape because your eyes adjust, and because there is nothing here to absorb light and nothing at all in the way. And ahead of you, on the plain, there is a column. It rises straight up off the ice, dark against the frost, absolutely vertical, for about 8 kilometers. Then, at the top, it stops rising and bends over sharply, as though it has hit a ceiling, because it has met a wind in an atmosphere 100,000th as dense as the air in your lungs, and that thread of dark material is drawn out downwind for 150 kilometres, laying a long dark streak across the ice. That is what Voyager 2 photographed in 1989, plumes of nitrogen gas and dark particles erupting on a world at 38 Kelvin in almost no sunlight. Something down there is putting energy into the surface. Whether it is a solid-state greenhouse effect, sunlight passing through translucent nitrogen ice and warming the dark layer beneath until the pressure blows out, or tidal heating from Triton's capture, or something else entirely, has never been settled, because nothing has ever been back to look. Triton is also doomed, in a leisurely way. That retrograde orbit is unstable against tides. Neptune is slowly drawing it inward, and in something like 3,500 million years Triton will cross the point at which Neptune's gravity can tear it apart, and it will become a ring system considerably grander than Saturn's. Neptune, meanwhile, has one more quiet horror attached to it that has nothing to do with weather or moons. One-way light time from Earth is about 4 hours. Say something into a microphone here, and it arrives there 4 hours later. Any reply arrives back 4 hours after that. 8 hours for a single exchange. Most of a working day for one round trip of the shortest possible sentence. Every world takes something different. Neptune takes the entire idea of being in contact with anyone, and that is the last planet. We have gone all the way out, 8 worlds, 8 walls, and every single one of them refused us for a completely different reason. Energy, duration, a machine, radiation, ground, decades, and now distance made into silence. So which one was it? Which planet is the one you never come back from? The answer, I am afraid, is none of them. And the reason why is going to take us back to something that has been sitting in the crew compartment the entire journey from the moment we left Earth, quietly running down. Every single thing we have talked about tonight has been a property of a place. Mercury's gravity well, Venus's pressure, Mars's dust, Jupiter's field, Saturn's absent ground, Uranus's decades, Neptune's silence, 8 worlds, 8 walls, and every wall belonging to the world it stands in. Now I want to take all of that away and talk about the one thing on the vehicle that is the same at every single destination, that does not care where you're going, and that has been degrading continuously since the moment the engines cut off. The crew. We are extremely good at building things that survive space. We are not good at building people who survive space, and the reason is that we did not build people. People were assembled over about 4,000 million years by a process that only ever had access to one set of conditions: one gravitational field, one magnetic field, one atmosphere, one star at one distance. Every system in your body is calibrated to those numbers. Take any of them away and things start unwinding quietly, in ways that were not obvious until we had people up there long enough to measure it. Start with bone, because bone is the most straightforward and the most alarming. Your skeleton is not a scaffold. It is a living tissue in continuous negotiation with the loads placed on it, constantly being dissolved and rebuilt by 2 populations of cells that respond to mechanical stress. Load a bone, and it thickens. Unload it, and the body, which is nothing if not efficient, concludes that the material is not needed and takes it back. In weightlessness, the weight-bearing parts of the skeleton, the hips, the lumbar spine, the bones of the legs, are unloaded completely, and they respond exactly as you would expect. Astronauts on missions of 4 to 6 months lose bone mineral density in those regions at an averaged rate of between 1 and 1.5% per month. Per month. That is not a typo, and it is worth converting into something you can feel. On Earth, an older adult with osteoporosis might lose 1 to 2% of bone density in a year, and we consider that a serious medical condition requiring treatment. An astronaut can lose that in 4 weeks. They fight it. Crews on the space station exercise for something like 2 to 2.5 hours every day. Resistive exercise, treadmill with a harness pulling them down, cycle ergometer, and it is not optional, and it is not for fitness. It is a countermeasure, and it works, in the sense that it slows the loss substantially. It does not stop it. And a Mars mission is not 4 to 6 months. It is 6 to 9 months out, a year and a half at 38% gravity, and 6 to 9 months back. Then there are the eyes, and this one genuinely surprised everybody. On Earth, gravity keeps a certain amount of your blood and other fluid in your lower body. Remove gravity and all of that migrates upward and stays there. Crews describe the sensation as a permanent head cold, puffy face, blocked sinuses, thin legs. That much was known from the earliest flights and dismissed as a nuisance. What was not known until people started staying up for many months at a time is that the pressure changes inside the skull do something structural to the eye. The condition is now called spaceflight-associated neuroocular syndrome. It involves swelling of the optic disc where the nerve enters the eye, folds appearing in the retina, a flattening of the back of the eyeball itself, and measurable shifts in a person's prescription. Approximately 66% of long-duration astronauts show at least one of those signs during or immediately after flight, 2 out of 3, and in some cases the changes have not entirely reversed after return. Think about what that means as an engineering statement rather than a medical one. We put people in a sealed can in weightlessness for 6 months, and the shape of their eyes changes. Not their eyesight, the shape of the organ. Something that we assumed was fixed architecture turns out to be quietly dependent on a force we never thought to include in the specification. There is more, and it accumulates. Muscle atrophies, particularly the postural muscles that spend their whole lives on Earth, resisting gravity without being asked. The immune system becomes dysregulated, and latent viruses that a healthy body normally keeps permanently suppressed, the herpes family among others, reactivate in flight at elevated rates. Bone demineralization puts extra calcium into the urine, which raises the risk of kidney stones, and a kidney stone is an extremely bad thing to develop several 100 million kilometers from a hospital. Scott Kelly's 340-day mission and the twin study that came out of it documented changes in gene expression, in telomere length, in the gut microbiome, and in cognitive performance, most of which returned to baseline within 6 months of landing. Most, not all, and underneath all of it, unremarked, invisible, without sensation, there is the radiation. I want to give you the number because it is a measurement and not an estimate, and I think that matters. When the Curiosity rover flew to Mars, it carried an instrument called the Radiation Assessment Detector, and that instrument was switched on for the crews, inside the spacecraft, behind the same structure that a crew would be behind. Over a 253-day journey covering 560 million kilometers, it measured an average of about 1.8 millisieverts of galactic cosmic radiation per day. Extrapolate that to the shortest realistic round trip using current propulsion and comparable shielding, and you get a dose equivalent of 0.66 sieverts, with an uncertainty of about 0.12 either way. That is for the transit alone. It does not include a single day spent on the surface of Mars. For scale, a chest X-ray is about 0.1 millisieverts. An abdominal computed tomography scan is around 10. The annual limit for a radiation worker on Earth is typically 20 millisieverts. The round trip to Mars is 660. And here is the part that has no engineering answer yet. Galactic cosmic rays are not the sort of radiation you can simply block. They are heavy atomic nuclei, iron, carbon, oxygen, travelling at a substantial fraction of the speed of light, carrying energies that make them very difficult to stop. When one of them strikes a shielding layer, it does not simply stop. It shatters, producing a shower of secondary particles that continue onward, which means that adding a moderate amount of shielding can, under some conditions, deliver a higher dose to the person behind it than no shielding at all. To reliably help, you need a great deal of mass, meters of water or polyethylene wrapped around the habitable volume, and mass is the one currency this entire video has been about running out of. The space station does not have this problem, and it is important to understand why, because it explains why decades of successful long-duration flight do not tell us what we need to know. The station orbits inside Earth's magnetosphere, which deflects the overwhelming majority of galactic cosmic radiation before it ever arrives. Everything we have learned about humans in space for the last quarter of a century has been learned inside our planet's magnetic shelter. A crew going to Mars steps outside it on day 1 and does not come back inside for years. Space agencies set career exposure limits for astronauts, and the way they are defined is unusually candid. Rather than a simple dose ceiling, the limit is expressed as a maximum acceptable increase in lifetime risk of dying from a radiation-induced cancer, commonly set at 3%. It is an honest way to write a rule because it admits what is actually being traded. And depending on which risk model you apply, and on the age and sex of the individual, a single Mars mission approaches that limit or exceeds it outright. It is not that we do not know how dangerous it is. It is that we have written down the number, and it is uncomfortably close to the number the mission requires. There is one more gap in the evidence, and it is a large one that almost nobody mentions. The longest continuous spaceflight any human being has ever completed was Valery Polyakov's 437 days aboard the Mir station, which ended in March 1995. More than 30 years later, that record still stands. Now compare it to a conjunction-class Mars mission. 6 to 9 months out and 6 to 9 months back is, by itself, between 12 and 18 months of transit, and that is before the 500 days on the surface. The transit legs alone are comparable to the longest anyone has ever been continuously off this planet, and the full mission is roughly twice as long again. And we genuinely do not know what happens in between 0 gravity and 1. Every piece of long-duration human data we possess comes from weightlessness. Nobody has ever spent more than 3 days in the 38% gravity of Mars or the 16% of the Moon. Whether partial gravity halts bone loss, or slows it, or barely touches it, is a question we have never had the opportunity to ask, and the first crew to Mars will be the experiment. So let me come back to that phrase I've been repeating all night, because it is time to break it. Every world takes something different. That has been true, and we have watched it be true 8 times. Mercury took energy, Venus took time on the surface, Mars took a machine that does not exist. Jupiter took shielding we cannot carry, Saturn took ground, Uranus took decades, Neptune took contact. But that phrase is only true of the vehicle. Every world takes something different from the ship. Every world takes exactly the same thing from the person. Bone, at 1 to 1.5% a month, regardless of destination. Eyes reshaping in 2 out of 3 people, regardless of destination. Immune function drifting, muscle going. And 1.8 millisieverts a day, every day, from the moment you leave the magnetosphere until the moment you come back inside it, identical at Mars and at Jupiter and at Neptune. Because galactic cosmic rays do not come from any of those places. They come from everywhere. And this is the thing I keep circling, and I want to say it as plainly as I can. Every other component of an interplanetary mission has a spare, a workaround, a patch, a redundant path, or a manual override. If a pump fails, you fit the backup. If software crashes, you reboot it. If a panel cracks, you patch it. There is not one component of that vehicle that cannot, in principle, be replaced or repaired or worked around. Except one. The astronaut is not the operator of the spacecraft. The astronaut is the part of the spacecraft that is being spent. And unlike everything else aboard, there is no spare, no patch, no redundant path, and no way to stop the meter, because the meter is not measuring the mission, it is measuring them. Which leaves one last thing to talk about before we can answer the question we started with, and it is the strangest cost of all, because it is not physical at all. There is a moment on any journey outward from Earth that nobody has ever actually experienced, and I think about it more than is probably healthy. It is the moment when conversation ends, not communication. Communication continues perfectly well. Radio does not care how far it goes, and with a large enough antenna you can hear a spacecraft at the edge of the solar system whispering at a fraction of a watt. What ends is the specific thing we mean when we say we spoke to someone, the back and forth, the overlap, the interruption, the correction, the laugh arriving in the right place. Light travels at just under 300,000 kilometers per second, which on Earth means that everything is effectively instantaneous. From the Moon, the delay is about 1.25 seconds each way. Noticeable, awkward, like a bad phone line, but survivable. The Apollo transcripts have that stutter in them if you listen for it. Go further and it stops being a stutter and becomes a wall. At Mars, one-way light time ranges from about 3 minutes at closest approach to about 22 minutes, when the 2 planets are on opposite sides of the Sun. A question and its answer at worst take 3/4 of an hour. At Jupiter, one-way time runs roughly 35 to 52 minutes. At Saturn, about 68 to 84. At Neptune, around 4 hours each way, 8 hours for a single exchange. What that means, practically, is that everybody out there is alone. Not lonely, necessarily. Alone in the operational sense. They can be advised. They cannot be helped. Every piece of guidance that arrives from Earth is guidance about a situation that no longer exists, formulated by people looking at data that was already old when they received it, addressed to a crew whose circumstances have moved on while the message was in flight. And the reverse is worse. Consider what happens if something goes wrong. Somebody sends a message saying there is a problem. That message crosses the gulf at the speed of light, taking however many minutes it takes, and arrives at a control room where the best people alive begin working on it. And by the time they have anything to say, the situation on the ship has already resolved. Either the crew fixed it, or they did not. Every emergency in deep space is over before the first person at home learns that it began. Everyone on Earth is a spectator at events that have already finished, watching them arrive in slow motion, unable to touch them. This is the third of the great weights of this journey, and unlike the others, it does not appear on any engineering diagram. Because here is the human version of that fact. On a mission to Mars, a crew member's family sends them a message. It is not a call. There is no such thing as a call at that distance. It is a recording, made at home in the evening, by people who love them. It travels for anything between 3 and 22 minutes and arrives, and they watch it. And every single thing in it is already old. The person who recorded it has already gone to bed, already woken up, already had a day that the recipient knows nothing about. They are being spoken to by a version of the people they love that no longer exists, about a version of themselves that no longer exists either. At Neptune, that gap is 4 hours in each direction. There is no meaningful sense in which the crew and their families are living in the same present tense. They are simply two groups of people transmitting messages into each other's past. There is an operational consequence of this that changes what a crew has to be. Every crewed mission ever flown has been run, in the end, from the ground. Astronauts are extraordinarily capable people, but the architecture of human spaceflight assumes a large team on Earth, with more instruments, more analysts and more time, watching the vehicle continuously, and telling the crew what the vehicle is doing. That model works out to about the distance of the Moon, and past that it simply stops. A Mars crew has to be its own mission control, its own medical department, its own engineering team, and its own final authority on every decision for years, and the people on the ground become advisors writing letters rather than controllers giving instructions. We have tried to rehearse this on Earth, and the rehearsals are revealing precisely because they are so much easier than the real thing. There have been isolation studies in which crews spent well over a year sealed in a mock spacecraft with simulated communication delays and no way out. There are Antarctic stations where a small group winters over in total darkness, cut off by weather for months, unable to be evacuated even in a medical emergency. Both of those are used as analogues, and both of them are gentler than the real case in one crucial respect. In both, you are on Earth. The air outside is breathable, the gravity is correct, and the isolation is a rule rather than a fact of physics. It can be broken if things get bad enough. Out there, it cannot be broken at all, and the signal itself gets extraordinarily faint. The radio power arriving at Earth from the most distant spacecraft we operate is measured in fractions of a billionth of a watt. To hear that at all, we use dishes 70 meters across, cooled receivers, and a network of stations spread around the planet so that at least one of them always has the target in the sky. Every fact in this video from beyond Mars arrived on Earth as a whisper at that level, painstakingly reassembled. The connection to a crew out there would be no different in kind, thin, slow, delayed, and utterly precious. And there is one more thing, which happened to the Apollo crews and has never happened to anyone since, and which will happen again to whoever leaves next. At a certain point on the way out, Earth stops being a place and becomes an object. It shrinks from a world filling the window to a disk, to a blue-white dot indistinguishable from a bright star. Every human being who has ever lived, every conversation ever had, every place anyone in the crew has ever been, is contained in a point of light that they could cover with a thumbnail held at arm's length. Voyager 1 photographed exactly that in 1990. Looking back from beyond Neptune's orbit, an Earth came out as a single pale pixel sitting in a band of scattered sunlight. It is a famous image, and it is usually presented as a lesson in humility. I think for a crew, it would be something rather different. It would be the moment where the thing you are trying to get back to becomes small enough to lose. We have now assembled everything. We have walked past 8 planets and named the wall at each of them. We have looked at the crew and found the one component that cannot be replaced. And we have found the third thing, the one that has no mass at all, which is that past a certain distance nobody can reach you, in either direction, ever again, no matter how much either party wants to. So it is time to answer the question we started with, and I want to answer it plainly, because I said I would. Which planet is the one you never come back from? The honest answer is that the question contains a mistake, and the mistake is the most interesting thing in this entire video. There is no such planet. It is not Mercury, and it is not Venus, and it is not Mars. And the reason there is no such planet is that the thing that stops you coming back is not located at a planet at all. It never was. It has been in the vehicle with you since the day you left, and it is the same thing at all 8 of them wearing 8 different masks, and once you see it, you cannot stop seeing it. Here is the answer, and it is very simple once it is said out loud. Every one of those 8 walls is a way of running out of time. That sounds like a rhetorical flourish, so let me do the work and show you that it is not. Let me take them back one at a time and translate each of them, and I think by the end you will find that they were never 8 different problems at all. Mercury's wall was energy, propellant, the delta V to climb back out of the sun's gravity well from a world with nothing to help you. But what is propellant? Propellant is stored time. It is the number of maneuvers you are permitted to make before you can no longer change what happens to you. A vehicle with full tanks has options. A vehicle with empty tanks is simply an object on a fixed path, and it will go where the mathematics says regardless of anyone's intentions. Every burn spends a little of the future. When the propellant is gone, the future has been spent, and the trajectory you are on is the only one you will ever have. Venus's wall was 127 minutes. That one barely needs translating. It is a clock, quite literally, a stopwatch running on a machine while the heat works inward, and when it reaches the end, the machine stops. We did not fail on Venus because the physics forbade us. We failed because we ran out of minutes. Mars's wall was a machine that has never been built, and a machine that must sit alone for years and then work once, on a date fixed by orbital geometry, is a clock too. The synodic window comes round every 25.6 months whether or not anyone is ready. Miss it, and you have not lost a rocket. You have lost 2 years. Jupiter's wall was radiation, and this is the one where the translation is most exact because dose is not a quantity at all. Dose is a rate multiplied by a duration. Nothing about the Jovian environment kills you instantly. It kills you at so many sieverts per day. Shielding does not remove the danger, it slows the accumulation, which is to say, shielding is not protection, it is borrowed time. Every centimetre of titanium buys hours. Enough of it buys a mission. None of it buys forever. Saturn's wall was the absence of ground, which resolved into 6 years out and 6 years back, keeping hardware alive at 94 Kelvin in the meantime. Uranus's wall was decades outright, a mission that consumes the working life of the people who fly it, and most of the working life of the people who built it. Neptune's wall was 4 hours each way, which is time in its purest and cruelest form, not a delay in a conversation, but a permanent offset between 2 presents that can never be brought into alignment. And the crew. The crew was the clearest case of all, and I saved it deliberately. 1 to 1.5% of bone per month, 1.8 millisieverts per day, 2 out of 3 sets of eyes changing shape over the course of a long mission. Not one of those is a threshold you cross. Every single one is a rate. The body is not damaged by space. The body is spent by space, continuously, at a known speed, from the moment the engines cut off. Propellant is stored time, shielding is borrowed time, consumables are counted time, a launch window is assigned time, and a human being is time that cannot be replenished by any means we know. So the planets do not actually differ in what defeats a return. They differ only in which clock they run down first. That is what would really happen on a journey to each planet. You would arrive at all of them, probably eventually, because arriving is the half we're good at. And at each one you would discover that something had been quietly counting the entire time you were travelling, and that the thing which stops you coming home is not out there at all. It is the same thing that stops everything. And I want to end somewhere quiet because there is one last version of this that has nothing to do with rockets. Imagine the mission works. Everything holds. The ascent vehicle lights on the first attempt, the transfer is clean, the capsule finds the atmosphere at the right angle, and the parachutes open, and after nearly 3 years a hatch is cracked open somewhere on Earth, and ordinary air comes in. They cannot stand. That much we know for certain, because we know it already from the space station. Crews come back and they are carried, because the legs will not accept the load, and the inner ear has forgotten which way is down, and the heart has spent years pumping against nothing. Somebody puts their hands under the arms and lifts. The weight of a body arrives all at once, after years of absence, and it is enormous. The bone that is missing is missing. Some of it will come back, not all of it. There is a long moment before anything else happens, and it is a strange one. For years, every sound has been machinery. Pumps, fans, the low continuous hum of a life support system that never once stopped, because if it had stopped, everyone would have died. That hum has been the background of every thought, every meal, every conversation, every attempt at sleep, for 1,000 days. And now it is gone, and what is underneath it is birdsong or traffic or wind moving through something, and the absence of that hum is louder than the hum ever was, and the sky is the wrong size. For years the sky has been a window, a rectangle of it, framed and finite, with a defined edge you could put your hand past. Now it goes all the way round, in every direction, unbroken, further than anything has any right to go, and there is no edge to it anywhere, and the blue of it is a colour that does not exist anywhere else in the solar system, and that nobody on that stretcher has seen since before the mission began. And the light is wrong, and the air is full of things, grass, diesel, salt, somebody's perfume, after years of breathing the same recycled volume, and there is wind on the face, which is a sensation nobody has felt in a very long time, and the world has moved. Everyone is nearly 3 years older. Somebody has been born and somebody has died, and neither event could be attended. The messages that arrived, the whole way out and the whole way back, were always 4 hours or 20 minutes late, and now they are on time, and being on time is the strangest part of all of it. The conversation is instant again. It has not been instant in years, and the person lying on that stretcher, blinking in the light, arrived. That is not in question. They came back. But the person who left is not on that stretcher, and never will be. The person who left is somewhere along a trajectory that no longer exists, in a body that had all its bone, in a present tense shared with everybody they loved, and there is no return journey to that. There never was. There is no vehicle for it, and no window for it, and no amount of propellant that would buy it. That is the trap. Not Mercury, not Venus, not Mars, not the giants. The trap is that a journey is not a line out and a line back. It is a segment of a life spent somewhere else, and the only currency any of it was ever paid in was time, and time does not have a return leg. Arrival is cheap, departure is not, and the most expensive departure any of those crews will ever make is not the one from Mars or Titan or Triton. It is the one from Earth on the first morning, when the engines light and the count starts, and nobody thinks to mark it as the moment they left. You never really come back. Not from any of them. Not from anywhere. And here is the part I did not expect to find when I started putting this together, and which I think is not bleak at all, though it took me a while to hear it that way. None of this is unique to spaceflight. Everything I have just described about a crew on a 3-year mission is true, at a gentler rate, of everyone listening to this. The clock does not start when the engines light. It has been running the whole time. Nobody gets to return to the version of themselves that existed at the start of anything. A journey, a year, a conversation. We simply live at a distance from that fact most days, because our own light delay is short enough that we forget there is one. The astronauts do not have a different condition from ours. They have a legible one. They can see the meter. They know the rate. Somebody in a control room has written down, in millisieverts per day, and in percent of bone per month, the price of where they are going, and they went anyway, knowing the figure, because there was something out there worth what it cost. That is not a tragedy. I think that might be the most admirable thing our species does. So the next time somebody tells you how far away Mars is, or how many years to Neptune, you will know that they are quoting the wrong number entirely, and that the real one is not written in kilometers, and never was, and is being spent right now by all of us sitting perfectly still. Sleep well,